Ever wondered how the universe works at its most fundamental level? It's a question that has intrigued humans for centuries, sparking a quest to understand the nature of reality itself. This curiosity led to the birth of quantum mechanics, a branch of physics that attempts to describe the behavior of the universe at its smallest scales. We're talking about the realm of atoms and subatomic particles here, where the conventional laws of physics seem to take a back seat. In this strange world, particles can exist in multiple places at once, and they can even teleport through barriers. It's a bit like stepping into a science fiction movie, isn't it? But how do we make sense of these bizarre phenomena? Enter the Dirac equation, a mathematical marvel that plays a crucial role in quantum mechanics. Named after the British physicist Paul Dirac, this equation is one of the crowning achievements of quantum mechanics. Today, we'll delve into its intriguing details. The Dirac equation didn't just appear out of thin air, it has its roots in the genius mind of Paul Dirac. Born in the early 20th century, Dirac was a British physicist, known for his profound contributions to the field of quantum mechanics. His thirst for knowledge and understanding led him to an intriguing problem that perplexed the scientific community of his time. Quantum mechanics and special relativity were two groundbreaking theories that revolutionized our understanding of the universe. Yet, there was a glaring issue. These two theories seemed incompatible. Quantum mechanics explained the behavior of microscopic particles, while special relativity described the rules of the universe at high speeds, close to the speed of light. But when you tried to apply quantum mechanics in a relativistic context, the math just didn't work. Paul Dirac was not one to back down from a challenge. He was determined to reconcile these two theories. His motivation? A belief in the elegance and simplicity of nature. He held that the laws governing the universe should be beautiful and harmonious, and this belief guided his research. Dirac worked tirelessly, poring over equations and pondering over the problem. His efforts culminated in the birth of a new equation, one that would bear his name, the Dirac equation. This equation elegantly combined quantum mechanics and special relativity into a single harmonious framework. It was a monumental achievement that demonstrated Dirac's brilliance and creativity. But the Dirac equation was not just a mathematical triumph, it was a testament to Dirac's philosophy of physics. It echoed his belief in the beauty and simplicity of the laws of nature. It was a beacon of hope that signaled the possibility of a unified theory, one that could explain the entire universe. Dirac's pursuit for a unified theory led him to formulate an equation that still bears his name today. The Dirac equation stands as a testament to his genius and determination, a symbol of the power of human intellect to unravel the mysteries of the universe. The Dirac equation, though complex, can be broken down into simpler, more understandable components. Let's start with the basic form of the equation. In its simplest form, the Dirac equation looks like this: IHDPS dt equals sine mc2p's. This equation might look intimidating at first, but let's take a closer look. First, there's PSIE, the wave function. This wave function is a mathematical description of the quantum state of a system. In the context of the Dirac equation, the system is the electron. This wave function is a complex number, meaning it has both a real and an imaginary part, and it evolves over time according to the equation. Next we have the Dirac matrices. These are a set of four 4x4 matrices that appear in the Dirac equation. They're named after Paul Dirac, the physicist who first introduced them. These matrices are unique because they satisfy certain mathematical properties that are crucial for the equation to work. Now let's talk about the relativistic energy-momentum relation. This is a fundamental concept in physics that relates the energy of a particle to its momentum and its rest mass. The relation is expressed in the equation E equals sine mc2 plus pc, where E is the energy, m is the mass, c is the speed of light, and p is the momentum. This relation is the backbone of the Dirac equation, and is what allows it to describe relativistic particles. Finally, there's I. This is the product of the imaginary unit I and the reduced Planck constant h. This constant is a fundamental quantity in quantum mechanics, and it shows up in the Dirac equation because the equation is rooted in the principles of quantum mechanics. So, to sum up, the Dirac equation describes the behavior of electrons in terms of their wave function, the Dirac matrices, and the relativistic energy-momentum relation, all tied together with the fundamental constant h. By now you should have a basic understanding of the components that make up the Dirac equation. The Dirac equation is not just a mathematical expression, it has profound implications that have shaped our understanding of the universe. This equation, born from the mind of Paul Dirac, has the power to predict phenomena that were unheard of at the time of its conception. One of these predictions is antimatter, yes, the stuff of science fiction. The Dirac equation suggested that for every particle, there exists an antiparticle with the same mass but opposite charge. This prediction was confirmed with the discovery of the positron, the antiparticle of the electron, showing that our universe is far more symmetrical and strange than we once thought. The Dirac equation also found its use in various fields of physics. It underpins quantum electrodynamics, the theory that describes how light and matter interact, and it plays a key role in the standard model of particle physics, our most successful theory of the fundamental forces in particles. The Dirac equation, beyond its mathematical complexity, offers us a unique peek into the fundamental workings of the universe. The Dirac equation is a complex but fascinating piece of quantum mechanics. Born from the mind of Paul Dirac, it serves as a cornerstone in the world of quantum physics. It perfectly blends the principles of quantum mechanics and the theory of relativity, offering a glimpse into the intricate dance of particles at the smallest scales. We've delved deep into its components, exploring the wave function, the Dirac matrices, and the clever mathematical tricks that allow us to unravel the equation's secrets. We've seen how the Dirac equation has shaped our understanding of the universe, from predicting the existence of antimatter to explaining the behavior of electrons in magnetic fields. The implications of the Dirac equation are profound, touching everything from the electronics that power our world to the fundamental fabric of reality itself. With every equation we unravel, we step closer to understanding the enigmatic language of the universe. And the Dirac equation is a crucial part of that journey.